this is work done in collaboration with current graduate student, Stathis Megas, and then former graduate student, Alec Krishnan, who's now at Kentucky. And so here is the archive number if you're interested. And so the general topic here is a basic one, and part of what the goal of this work, of this talk, is to attack a well-known problem, try to simplify it as much as possible to develop some efficient methods, but ones that are also actually quite straightforward and easy to describe. So I'm hoping, oopsie, did my screen just disappear?
Yeah, something happened, so maybe you can try once more. Sorry.
Okay, huh. That's weird. Doesn't really happen that quickly.
Yeah,
it's okay now.
Yeah, it's back.
It's a bad, okay, good. It's a bad omen that happened that quickly. But anyway, so hopefully this talk will be relatively pedagogical, at least until possibly the very end. But okay, so the general goal here is we have some, imagine some weakly coupled quantum field theory in AdS of arbitrary dimension. And I want to compute the spectrum of that theory, by which I mean we'll be working, say, in global AdS, and so we have the usual Hamiltonian of global time translations. I like to know the spectrum of that Hamiltonian, and along with the other quantum numbers, angular momentum, and so on. Okay, so well, this is just an interesting quantum field theory question by itself, but it's also then very relevant to AdS CFT, of course, because if one computes the spectrum of energies in AdS, energy again with respect to global time, then as I'm sure we all know, this maps by AdS CFT to the spectrum of operator dimensions in the conformal field theory. So for every energy in AdS, there's a energy, there's an operator in the CFT whose dimension equals that energy. So in the context of this talk, I'm just thinking about writing down some particular quantum field theory in AdS. So we're taking a bottom-up approach. I'm not worrying about whether this comes from string theory or whatever. But we know that if you do that, and if there's some small parameter in that theory, some expansion parameter, you write down any local action in AdS and use that to compute boundary correlators, then those correlators will obey the axioms of CFT. So in particular, the expansion, that small coupling, will translate on the CFT side to some sort of expansion, which we normally call a 1 over n expansion, whether that's literally an n of a gauge theory or not. It's irrelevant, we call it 1 over n. So we can construct at least a 1 over n expansion of CFT like this. And of course, you just write down some random theory most of the time. That 1 over n expansion may or may not actually have a finite n completion, but that's not something we're going to worry about here. Okay, so this perspective, of course, was especially developed in this famous paper by Heemskerk, Polchinski, and Sully. Furthermore, I'm just going to be looking at low energy states here. So states just close to the vacuum. So these will be particle states. And so we're not going to be discussing anything to do with black holes or brains, et cetera, and then non-perturbative objects. We're just doing perturbation theory of the low energy spectrum. Okay, so this is a very well-known problem, and especially of a lot of work on this in the context of AdS CFT. And then the standard approach to this problem, to working out the spectrum, is by expanding correlation functions, boundary correlation functions, say a 4-point function. So I'll say more on this later, but when we say compute a boundary 4-point function and then expand that into conformal blocks, and you do that expansion, you can read off the data. And you read off the dimensions of operators which are exchanged, and also their couplings to the external states, which are the coefficients. Okay, so this is a principle well-defined, principle straightforward procedure, but it gets quite technical, as we'll mention later on. And so instead, I'm going to try to use not the endpoint correlator, but just compute the partition function, the thermal partition function. I'll try to extract this data. And well, one thing to say is, and so the hope is this might be simpler, and one reason to expect this might be simpler is that in this other approach where you expand a 4-point function, you get out, as I said, both the spectrum of operator dimensions and OBE coefficients, okay? Whereas here, this can be the partition function or the, the 0-point function. This will just lead to the spectrum of operator dimensions. So it'll be blind to OBE coefficients because we don't have any couplings of external operators to be coupling. So we're computing half as much information, so you might expect by some sort of conservation law, this might be like half as difficult or something like that. So anyway, so we'll see that indeed it is, if you want to know the spectrum itself, this is a much simpler and straightforward approach, at least for certain types of problems. We haven't explored this in detail, so I shouldn't say it as a global statement, but the things we're talking about here. Okay, so let me begin with, so that was, let me start building this up, and a bunch of this will be review that will be familiar to many people. So let's start by talking about a free theory in the bulk before we turn to interaction. Let's just review the situation where we have a free field in the bulk, and let's take that to be a scalar, okay, free scalar field. And so it's free, so in the CFT, we want to think of that as being the n equals infinity limit. Okay, so right, so here are the usual picture of global AdS, and I'm gonna always set the AdS radius to 1 here, and there's always time runs up like this, and then we get into the directions. Okay, so so when we quantize the free scalar field, we just solve the wave equation, find a complete set of modes, and then attach creation annihilation operators to each mode solution. So this is a well-known problem. So we have some mode solutions, each of which has some definite frequency with respect to global time. So there's some labels here. There's an N label, an L label. The N label is essentially the radial excitation, how fast the thing is wiggling in the radial direction, and then there's some angular quantum numbers. L here is sort of a shorthand for all of the angular information, so the L's and N's and so on. Okay, so then when you solve this problem, you find the, if you demand smoothness and normalizability and so on, you find the spectrum of allowed energies is given by a delta, which is related to the mass of the scalar field like this. And then there's integers N and L, which both range from 0 to 1, 2, 3, etc. So that's the spectrum of single particle energies. Okay, and then on the CFT side, we should have a corresponding spectrum of operators. And so we arrange things by representations of the conformal group. And so we can start with some scalar primary operator of dimension, scaling dimension delta. And then we also have its conformal descendants. And so the conformal descendants are just derivatives of the primary. And the derivatives here, we can either track the derivatives, so we get a scalar type of operator into n of those, and then have 3 indices, L3 indices. We can take these guys to be symmetric and traceless. So there's really some symmetric traceless combination there. So so those are the CFT operators, and at least the ones that are dual to these single particle states. And then the map is very simple. So just each mode here, we have some creation operator. We hit that on the vacuum, we get a state, and that maps over on the CFT side to the corresponding operator with the same NL labels. We take this operator, hit that on the CFT vacuum, and then we declare these two states to be dual to each other. Okay, so that gives the complete tower of mapping of the single particle states built so that n equals L equals 0 is the primary state, and we have all the descendant states built on top of that. Okay, well, we can also, those are the single particle states. Now we can go to multi-particle states, and for here, all we need to be talking about really is 2 particle states. So we can have, again, in the free theory, you have 2 particles moving independently, so you just can tensor those together in a trivial way. But we'd like to additionally, since we'd like to additionally decompose that spectrum into representations of the symmetry group in question, so of the symmetry group of AdS, or the conformal group of the boundary CFT. And so we decompose things into 2 particle primary states and their descendants. And so the 2 particle primary states have, you might expect, these to be the energies. The label of those states are given by, we sum up the dimensions, and then again, you have these N and L, sort of the radial angular excitations of these two particle wave functions. And then on the CFT side, you build these double trace operators. So you take the product of these two single trace O's and sprinkle in some derivatives in between them like this, with particular double arrows here, derivatives acting to the left or right with relative minus sign. This is so that these things transform as primaries. And so then, of course, each derivative raises the conformal dimension by 1. And so then the operator dimension here is simply delta 1 plus delta 2 plus 2n plus L, which then of course matches that spectrum. Okay, so that's simple. So this is all, and then of course you could do the same thing here for 3 particle states, 4 particle states. So this is all, again, in the large N limits where you can reproduce the structure by computing a correlation function, a 4-point correlation function, expanding it. And that's, again, very simple because in this large N limit, correlators are just factorized. 4-point function, then that will factorize into 2-point functions like Witt's theorem. So these operators in the CFT, if they act like free fields, and that's sense the correlators factorize. Okay, so that's the story with the free theory. And now we want to turn on some interactions and ask how things change. So, so we turn on some small bulk coupling lambda. Again, we think of something like 1 over n in the CFT. And so now the 2 particle states, the energy of the 2 particle states are not simply the sums of the individual 1 particle states, but there's some binding energy or some repulsive or attractive interaction energy to the coupling. So each 2 particle state we had before will have its 0th order energy and then plus some small correction proportional to either lambda or lambda squared, defining the coupling. Okay, and so this small correction of the energy then, from the point of view of CFT, then we would call that the anomalous dimension of the operator. So we have this double trace operator, and its dimension would get shifted in 1 over n, and that shift gamma NL should match the bulk shift in the energy. So if you had some independent way of defining some AdS CFT proposed dual pair, then one check you could do, of course, would be to compute the spectrum energies in the bulk, the spectrum operator dimensions in the CFT, and compare those over the 1 over n expansion and check that these gammas include. Of course, in generalists, you'll know that's very hard to do because, well, it's a weak, strong coupling duality. So if you can do it on one side, you're going to need some special features like supersymmetry or some powerful computational techniques to do it on the other side. So anyway, that's the principal check. Here, the point is I'm not going to even be really talking about doing independent computations with CFT. I'm just going to be working entirely in the bulk. So given some bulk theory, I just want to develop some efficient methods for computing these anomalous dimensions using bulk perturbation theory. Okay. And that would supply data, I guess you could say, if one had some other way of computing things on the CFT side. Okay, so here is just a qualitative sketch of the standard way that this is done with a few comments. So as I said, the traditional way, going back to probably the first paper that actually did this was by Hong Liu, and then there's a paper by Friedman and Rostelli and so on, many people since. So it's to consider some boundary 4-point function here. So some operators O1 and O2, compute their 4-point function. And then we want to interpret that in CFT terms. Interpreting CFT terms means that we do the conformal block expansion. And from the point of view of CFT, that just means that we have an operator product expansion. So we can take a 4-point function and then pair together operators and then use the OPE to replace those by sum of, replacing sum of any pair of operators by sum over single operators. And that reduces everything to the 2-point function, and then you just use the normalization. So, so when you do it this way, you get this thing is expanded in terms of the OP coefficients, the coupling of operator 1 and 2 to some primary operator P. And then, again. So this is expanding in sort of the 1-2 goes to OP goes to 1-2 channel. And then there are these objects here, these conformal blocks, which are determined by ultimately by representation theory, somewhat nasty functions. If you have weak coupling here, you can just expand everything in sight in terms of your small coupling. So the OP coefficients have some expansion in terms of the small coupling, the operator dimensions, delta P's here, you'll have some expansion. So you expand everything and do perturbation theory on both sides and compare. And you can read off the data. So again, in principle, that's extremely straightforward, but in practice, if you just do this completely head on, it's extremely messy due to the fact that computing one of these correlators is by itself quite difficult, just essentially due to the fact that, well, the propagators themselves are typically some hypergeometric functions or something. You have to do these horrible integrals and so on, which can be in closed forms, so you do expansions and so on. And then these conformal blocks, well, in even boundary dimensions, they at least can be written in terms of hypergeometric functions, but odd dimensions, even that doesn't hold. Their recursion relations or sums and so on. But they're nasty things to work on. So it's very technically demanding to actually go and carry this out, even though it's conceptually very straightforward. So and again, we're just talking about tree level diagrams here. Things of course get worse if you try to go to the loop order. But then, so over the years, there've been many techniques to deal with this, many very powerful techniques, very nice techniques. So you can work in position space, you can go to melon space, for example. There's a lot of symmetry in this problem, so you can use that, which means using harmonic analysis. And then more recently, there's this Lorentzian inversion formula of Kerr and Quo, which essentially lets you, for certain types of diagrams, that you only compute your part of it. It's double discontinuity, which is a lot simpler, and so on. So there's a lot of technology, and so what I want to do is try to simplify things as much as possible. And powerful and lovely as these things are, it'd be nice to have some methods which don't require quite as much startup costs, you could say. That remains to be seen when you go to higher orders and that, which is more efficient, but it'd be nice to have some relatively elementary methods we can expect. So the method here, as I mentioned before, is we're going to just compute the partition function, just the thermal partition function. And so we'll look at AdS, global AdS at finite temperature beta. As usual, it means compactifying, identifying imaginary time by period beta. And so we're going to compute Z of beta, trace even minus beta H. And of course, this captures the spectrum of energies. Z of beta, you can expand it and you got the spectrum. In general here, of course, this is not the most general partition function. So we also have the SOD rotational group. So I could add in various chemical potentials here for momentum, if I want to keep track of that. And that, I wouldn't actually have to do that explicitly to get all the information I need. So actually it's going to be enough here to refer to the Z of beta, the simplest thing. So hopefully see as we go along. So, okay, now again, what I want to do here is not just sort of brute force expand this in terms of just e to the minus beta e's. I want to rearrange this. I want to read off the spectrum of primaries, right? Once I know the spectrum of primaries, then the representation theory tells me I know all of descendants. So I just like to capture the spectrum of primaries. And so what that means, I'd like to take the Z of beta and like to expand it into characters. So each character is the contribution to this trace from one representation. So if I can expand this in characters, then that will tell me the spectrum of primaries. So the character appears, I say, aha, that means there's that primary. And so I tried to expand the Z of beta here. And so I'll expand in all operator dimensions and all possible representations of an SOD. And so given operator dimension representation could appear with some multiplicity, these n's here, some integers, and then the characters. So, so these characters, we're just talking about this partition function just with temperature turned on, nothing else. Then these characters are extremely elementary to obtain because we just start with some primary state, some lowest energy state, some like lowest energy state of the Hamiltonian. And then the other states in that representation are just given by acting with the raising operators. So the raising operators in conformal group are just the momental operators. And so there are, so if we're in CFT-D, we have D of these, so they're D-independent P's that commute with each other. Each one raises the energy by 1 unit, so I apply K of them, I'll raise the energy by K. So these things, these commute, these act independently, so I can just sum up all the contributions, any number of each one, so holding decouples. And so I just get basically, well, this is just sort of the primary dimension, I just get D copies of the usual kind of thing you get for, non-separate bosons. And this D sub R here is just that whatever this representation R was will have some the ground has some degeneracy, and so there are D such states, and then each of those D sub R such states you just act with these. So these are the characters. They're just very explicit, simple objects. Okay, so you'd like to expand your Z of beta in terms of these quantities. Okay, so suppose we did that. Suppose we had that expansion.
Sorry.
Yes.
So just a question. So here you will be always talking about dimensions if they're greater than 2 in CFT, or so you're just considering the global conformal character.
Yeah. So even if I'm considering, yes, right, exactly. Even if I'm in D equal to 2, I'm only going to use the global conformal group. Okay. Correct. Yeah. So I'm going to do something that works for all dimensions uniformly. Like D equals 2, of course, one could think about Sorrow as well, but I'm not going to do anything.
Yeah, and in principle, you can also turn on chemical potentials for the angular momenta and so on, but you won't do that.
Well, as you see, I won't need to, because I'm not going to need the explicit. You'll sort of see why that's clear. So implicitly, I said I will, but I don't have to worry about that. If I did it here, part of the reason I'm doing that is to actually work out the explicit character chemical potentials turned on here. Then you get more complicated formulas that are written here. So I'm writing this out. I'm not actually going to need, as you'll see, the explicit form of these characters, because when I do my AdS results, it'll naturally be expanded in characters, even though I don't explicitly know what the characters are. That hopefully will become clear. But yes, indeed, the general character would have all of those potentials turned on.
Okay, thank you.
One other thing maybe you should say is that, so here, this is the generic character. So if you had, for example, like a massless spin 1 field or something in the bulk, then there's some null states corresponding to that. In fact, would be able to conserve current. So these are the general characters here that don't have any null states in the representation. But then that's always ever going to appear in this work here. So don't worry about that subtlety. Okay. Right. So yeah. Okay. So suppose I did this. Suppose I had this expansion. Now, suppose I did this in the free theory, and then perturbation theory in the small coupling. What would that affect? Well, so the only thing here, so these are integers, so they of course don't depend on the small coupling. Representations R don't depend on the small coupling. All that happens is the dimensions here, the dimensions that are appearing, spectral dimensions, those do depend on lambda. So if I want to take this and expand it lambda, what happens here is that I'll expand the chi's, the characters, with respect to delta, taking into account the lambda dependence of delta. So that's what I've written here. So the partition function will take its value in the free theory, lambda equals 0. And then here, this is just doing the first order Taylor series expansion of the chi's with respect to delta. And then the shift in delta, that again is gamma, the anomalous dimension. So if I only work to first order lambda, which is what I'm going to do here, first order. So I'm going to be considering like quartic type interactions at first order in lambda. And so those only affect 2 particle states, right? Since if I have a 3 particle state, I can't have a quartic interaction that acts non-trivially on that 3 particle. It won't mix all 3 particles together. So, so for our purposes, there's going to be some corrections to 2 particle states, and then states with more than 2 particles, their corrections to their dimensions will only get shifted at higher orders in lambda. So we're only going to worry about the 2 particle states here. And if you work to higher order lambda, you can consider more terms. Okay, so this is so in principle, if I have Z of beta and I can expand it in this form, then I just read off the gammas here. So the goal of this, so what I want to do is I'd like to find a way of computing things in the bulk such that Z of beta kind of naturally takes this form.
Can I ask something?
Yes.
Yeah, so why are the 1 particle states not corrected again?
Oh yeah, good. So the 1 particle states, I basically choose to have those remain uncorrected, because that's So what I'm really trying to do here is effectively compute the binding energy. I'm trying to compute the energies of two particle states in terms of the one particle energies. So I just by definition take the one particle states to be uncorrected. So it's an ambiguous question to ask what their correction is, because it's like a general sort of normalization question. And so you might say there's an infinite renormalization of the energy, but I express everything in terms of the energies of the one particle states. So that's the, I use that. You could, or if you like, another way of saying, you could say I'm going to add a counter term to shift away that energy to zero. But this is what one always does in these type of calculations. If you work at a double trace operator dimension in terms of the dimension of the single trace operator.
Okay, thank you.
Okay, so right. So I'd like to find a way of massaging the bulk z of beta, so it just takes this form automatically. And in particular, what it means, I want to avoid having to do any AdS integrals. So what I don't want to do is to go and explicitly compute z of beta in its full glory and then try to expand it into this form using the form of the cos. I like to sort of bypass all that, get the expansion to happen automatically. Okay, and so the main result here will be to show how to do that. But so I should say here, so just to set expectations. So right at the moment, we understand how to do this essentially for any quartic contact interaction here. We could have any number of interactions. And and this works nicely. Of course, the other, even at tree level, you can also have these exchange interactions, which at the moment we only have partial results on, so I'm not going to really talk about that. But for these guys, at least, things work quite nicely. Okay, so first I'm going to actually talk about how do you compute in the bulk, how do you compute the partition function just for the free theory. So this will give us, at the end, one useful result that we'll need. I'm not actually going to need all the information here, but part of the reason I want to do this actually is for pedagogical purpose. I actually have not seen, I was sort of surprised, I couldn't find anywhere in the literature that had computed, just for a free bulk scalar, computed thermal partition function from the path integral in the bulk for arbitrary dimensions. So there are sort of results there for particular dimensions and so on, for reasons I'll mention in a second, but just this is a basic problem, and so it's useful just to go through this. And the point is that, so the partition function of a free scalar, of course, just from the fact that we know the spectrum, it's sort of very simple to write down just by, you know, the spectrum, and so you can just compute the trace. You know, you can basically think of each mode of the free field. So each mode appears, you know, independently. So you basically, as usual, have some collection of harmonic oscillators. So the partition function is just a product over harmonic oscillator partition functions. But what I mean here is we want to do it from the path integral, because that's how we're going to arrange the calculations of the interacting bits. Okay, so anyway, so here's maybe just filling some gap in the literature here, but as I said, there'll be one formula at the end here, which I need for the remaining. So, okay, so again, I can be completely explicit here. So, so we just have some free scalar field action, again, mass related to the CFT operating motion like this. Okay, we're going to work in global coordinates with global time, maybe periodic, the period beta, and we just want to compute the path integral. Okay, so we do a series of standard manipulations here. So, okay, so the partition function, you know, quadratic actions, we get the determinant, we write that in terms of a trace log as usual. So the log of the partition function is trace log of the wave operator. And then I take this and I differentiate this with respect to the m squared parameter to get this. Okay, so the log there, so I get 1 over. And then this object here, of course, is the bulk propagator. Both matrix elements are the bulk propagator. So this is just the trace of the bulk propagator. And so then I take this expression here, integrate with respect to the mass, and so I get an expression for the log of the partition function equals the integral with respect to the mass of this. This is the trace of the propagator. So I take the two arguments of the propagator equal to each other and integrate over all points. That's what we mean. Integrate over thermal AdS, of course. So that's we mean this is the thermal propagator. This is the bulk propagator that's periodic, respects the periodicity there. Okay. Okay, and so thermal AdS is just given by making identifications. We can write down the thermal propagator just by sum over images of the global AdS propagator. That's what in here. So I have the thermal propagator G beta expressed in terms of the global AdS propagator like this, where we take one argument and call it y and beta. So y and beta just means the time argument there is shifted relative to x by n thermal translations. So, so this satisfies the wave equation and is periodic, so it does what it's supposed to do. So I just plug that into the partition function, and now we get the sum over n's of integrals of the propagator. Okay, so then at this point now, okay, now you want to actually go and evaluate this. So you'd like to do these integrals. Okay, and so this, everything up to now is just totally standard. I mean, it's like material. But now when you come to the integrals, if you just try to brute force do these integrals, it's pretty nasty because the standard expression for the Volokov propagator is this hypergeometric function here. So this is the solution of the wave equation with a delta function source. And sigma here is the geodesic distance between the points. So if you take this thing here and then plug into here and then try to carry out these x integrals, it's not a lot of fun. And you can probably do it in sufficiently low enough. Certain dimensions of the hypergeometric function can be expressed into elementary functions. You can probably do this. But not in general. And other things that have been done someplace in the literature are you can try to use like a heat kernel representation of this propagator and then try to carry things out. But in fact, heat kernel is only nice in even boundary dimension and odd boundary dimensions. Heat kernels are integral expressions themselves, and so it's pretty complicated. So after being surprised that it's done before, it eventually it turns out to be one nice representation of the propagator that lets you carry this out. And this is what you might call the spectral representation. I don't want to go into too much detail about this, but this is where you use, some of you might be familiar with this, use this thing called the split representation. This is basically using harmonic analysis, using this split representation of the propagator, and then you do a bunch of contour integral representations of that and so on. And so ultimately you get this expression. I'm not going to be using this at all, so don't worry about the details of this. This is just flashing here. But the point is there's one representation of the propagators for which all the dependence on the AdS coordinates just appears here. So this U, this is the only place where the AdS coordinates appear, U, and U is related to the geodesic distance like this. Okay, everything else is just a bunch of spectral integrals and contour integrals and so on, but all the dependence on the AdS stuff is there. And so that's so simple that you can now put this into here and then do the AdS integrals in the first step, and then after you've done that, everything becomes relatively simple. So you carry that out, whatever, and you get, after the dust clears, you get this result, which this result is is the known answer. This is what you get quite easily, in fact, just by writing down the spectrum and just compute the partition function by the sum of their states. Okay, so anyway, so part of that was to say, okay, yes, it can be done by the path integral, and that's how you do it. And okay, so now let's get to the point that we're actually going to use something here. So so again, we have this is this free theory. So we take this, we expand on the partition function. We should see it takes the form of expansion in characters of the known spectrum of single trace, double trace operators, and so on. And indeed, I mean, you can show that. So these are the characters here, and the relevant representations are, so the double trace operators. These would be symmetric, traceless tensors. And so, indeed, you can show that this thing can be expanded in those characters with the operator dimensions being 2 delta plus 2n plus j, which is the expected energies of the 2 particle primaries. And, well, these are 2 particle states built out of identical bosons, so you only get even angular momentum due to the Bose symmetry. Okay, so anyway, so that works fine. For us, what we need here is the fact that this first term here, this is the single particle contribution. And if you go back to where that came, that single particle contribution, so the sum n here was the sum over, we call it the sum over windings. That sum came when we built a thermal propagator up out of make identifications. So we think of each n as saying the propagator has been winding n times around the thermal circle. So the single particle contribution is just a single winding term, but this is just, so this is the character of this one representation. And so what we learned here is that the character is just given in terms of bulk objects like this. So you take the bulk propagator that winds once around the thermal circle, that's the key point, it winds once, so the 2 points are separated by a single thermal translation, integrated over AdS, integrate with respect to the mass. The mass here, of course, is related to the operator dimension here that appears there, and that gives you the character of the, well, here it's just a spinless representation, but the same thing holds in general. So here's the formula that I really want, is the characters, the expression for the characters of the arbitrary representation is given by, you take the propagator for the object of the corresponding mass and spin, trace it, take the single winding contribution, integrate that over AdS, integrate by the mass, that is the character. Okay, so this gives you the bulk representation of the character. So the logic of this is that we want to say, we have a bulk representation of that, so we can arrange the bulk perturbation theory to be in terms of these objects, and then I'll automatically have an expansion in terms of characters, even without having to, I don't have to evaluate this integral, because I know it gives the characters. Okay, so that's how I'm going to bypass the need to actually form AdS integrals, because I know if I did them, if I can get things in this form, I know if I did the integrals, they give me the characters. So I can do it explicitly. Okay, so right, so now we can go and apply this. Now you can sort of apply this to an actual case. So I'll start with the simplest possible case where you can really see everything. I mean, what's nice about this, again, is you can essentially do everything pretty much in real time. You can follow every step. It's really quite elementary. So the simplest possible situation is, yes?
Yeah, if I may interrupt. So is there a similar interpretation when you have more than one winding, like if, when n is greater than 1? Or, is it some conformal object from a CFT conformal representation theory?
Yeah, I don't think so. Actually, it's it can be expressed in terms of characters, but it's in terms of like it would be a linear combination of characters and products of characters. That's, yeah, so it's definitely not equal to a single character. You do like a double winding, so we can expand in terms of those, but it's not, I don't actually know if there's a general formula, but what I do know is it's not simply equal to a single character.
But it's not like some, n tensor products of this depth.
No, it's not quite that simple. No, there's sort of mixing between contributions from squares of single particle states and two particle states. These things kind of mix together. It has to do partly with the distinction between log Z or log Z and so on. So there are different sort of ways of expanding it. So yeah, it's a bit more complicated.
Am I right that if you write the nth binding state, and in terms of characters, you'll get minus signs? It's not really a character of a representation, but it's some kind of
correct. Yeah, exactly. So there'd be some. It's not a character. It's some linear combination of characters, indeed, with actually with minus signs. Yeah.
I think it'll be the. So this is Rajesh here. It's expressing trace u to the n in terms of the characters of u. There's this Frobenius type formula which relates trace of. So trace u to the n will be the nth winding sort of mode. And it's the group theory that relates trace u to the n to the way, just like trace u square will be written in terms of the symmetric and the traceless and piece and so on. So it would be that kind of decomposition, if I'm not mistaken. That's this multi-particling.
Yeah. Okay. That sounds right. Yes, thank you. Okay. Right. So coming back to here. So let's take two bulk scalars, phi1 and phi2. This is to make the combinatorics as simple as possible, and then the simplest quartic interaction. Okay. So I'd like to, and there's some coupling lambda. I'd like to be the anomalous dimensions to order that. Okay. So this is a very simple problem. So of course the answer is known. I don't remember, sorry, offhand who did this first, but this type of interaction, first of all, gives anomalous dimensions only for spin 0 double trace operators. And so there's some gamma n0, and then there's some formula here. Okay, expressed in terms of these are all Pock hammers, whatever. There's some nothing especially lovely about the result, but anyway, that's the answer extracted from the 4-point function or whatever any method you want to do. So yeah, so just look ahead. So again, a known fact as well. So if you have these interactions with no derivatives, those only give rise to spin 0 anomalous dimensions, whereas more generally, if you added in, say, 2J derivatives sprinkled in here somewhere, then you can get anomalous dimensions for non-zero spin double trace operators, but the maximal spin would be J. So with 2J derivatives, you get maximal spin J. You might get less than that depending how the indices are contracted, but that's the maximum you get. Okay, so let's see how to carry this out then. Okay, so we want to compute the partition function of this theory here to order lambda. So we just do elementary perturbation theory. So we just write down, log z, connected, generator connected correlators, and just bring down this to first order, and then we contract. So I just have, the product of these two bulk propagators and contract.
Hello, maybe.
Sorry.
Oh,
yeah, it seems like your screen is frozen.
Yeah, there.
Okay.
Okay, you should see it now, hopefully. Yes, okay, sorry. So that's what happens all the time. So, okay, I don't know where it started freezing, but the point was that we take this action here, compute the partition function, order lambda, just do width contractions, order first orders, we get the product. So we just have, anyway, the product of two bulk propagators integrated over AdS, order lambda. Okay, so then each one, the propagator is given by some image sum, but here, if we just want to look at, the only non-trivial thing that happens here at order lambda is a contribution to two particle states. There's some diagram like this. You can think of one of the guys comes here, the one comes here, and then they touch at this point. That's the only non-trivial thing that happens at this order. And so that means that in these image sums, we're only going to keep the terms at n equals plus or minus 1, because if it goes around again, it's not going to, again, that has to do with like 3 particle states and so on, but they don't get any independent contribution at this order. So, okay, so we take this and now just keep single winding contributions where it could be plus or minus 1. Well, the factor of 4 was from something overall then, and then I just have n equals 1 here. Okay, so now, again, I could in principle try to do this integral by straightforward, just try to compute the integral and express in terms of characters, but that would be the hard way of doing it. So the easy way to do this is to try to relate this directly to the characters. And for that, we want to do something that's kind of similar to the Sheldon-Lehman representation, where we're going to try to express this product of propagators in terms of single, linear in the propagators. Because linear in the propagators integrated, those were the characters. So now you can see that's possible because if we just take the product of two bulk propagators at points x and y, so they have the same x's here and the same y's, the endpoints of the system sort of thing like this, then you can think of this in terms of computing this expectation value of free fields. And then let's just put in some complete set of states in there, and the states that will contribute here are going to be fields, so there'll be some 2 particle states here. These primary dimensions and their descendants. And so it's just clear from putting this complete set of states here, this product will take the form of an expansion over propagators whose dimensions are given by these guys, and there'll be some expansion coefficients here. Okay, so you can expand the product to propagators with common endpoints in terms of these guys. There are many ways to think about this too. You can think about, you can just see that from the form of these functions that such an expansion has to exist. Or you can think of this from the fact these things satisfy differential equations. There's some sort of Sturm-Liouville type thing going on here, but in any different ways to think about this, there's this expansion. So I'll write down the coefficients here in a second, but they're easy to work out, those coefficients. Okay, so let's use that. So then so we use that in here. So this thing becomes a sum over single g's. And so that's what I've written here. This term now, here, I just have the sum over and the coefficients, and then sum over these propagators like this. But then I remember that this object here was, well, this object, an additional integration over mass was the character. So that means there's no integration with the mass here, so that essentially the derivative of the character with respect to the mass is given by this object. So here, but now I'm going to express that in terms of derivative with respect to the dimension, so there's some prefactor here. So essentially what this says is this object here is just the derivative of the character, and then I should divide out by this thing. That's what I've done here. Replace this by the derivative of the character, and then dividing by this is just dividing by this factor here. So this, I said before, this takes exactly the form I want to. Now the partition function is expanded in terms of derivatives of characters, and then the coefficients that appear here, shifts, are just the anomalous dimensions. Okay? Because they're the shift, they're giving you the shift in the energies. So what this says here is that the anomalous dimension, the real data in the anomalous dimensions is just coming from the expansion coefficients in this kind of formula. Expansion in terms of products of propagators, in terms of single propagators. And just to show you how that works in the simplest possible example, so if we go to b equals 2, so AdS3 CFT2, then the Both-Well propagator in this case is actually very simple. It's just given by this simple formula in terms of geodesic distance. And so it's just completely trivial to then take a product of two of these guys and expand it like this. It's just an elementary series you can imagine. And so you get this formula here, and so that means the coefficients are 1 to 2 pi. And so then you plug in the previous expression, you get these anomalous dimensions. So really the only, yeah, so you, in this case, you can sort of compute it without doing any real calculation at all, other than nothing's more difficult than summing the series, sum of x to the n. That's about it. So, but then again, so you can easily compute these coefficients, the a sub n's, for any dimension d, and then you get back these expressions here that were done that do indeed, of course, match the expressions from the 4-point functions. Okay, so everything else is just a elaboration on this method. So all the general ideas were actually given in that simple example, and then the other cases are just there's just a bit more indices and things like that flying around when you have derivative interactions. But the idea and the approach is exactly the same. It's really very straightforward. So, yeah, so the last part, yes, go.
Sorry. So this A and zeros, is there a way of characterizing them purely from the CFT? It seems like some representation theoretic object, right?
Yeah.
Can we get it without we were talking about AdS?
Good question. Yeah, I don't know. So in fact, we're going to have there's going to be a generalization of this, which I'm going to come to. So in the case of, I'll just mention the context of this. So the general case of derivative interactions, we're going to want is an expression which relates the derivatives. So the GS here means the sth derivative with respect to this u variable. And so the general form we're going to need here is the s derivative, product of the s derivatives of propagators can be expanded in terms of s derivatives of single propagators, some coefficients a and s. And then these things here, again, we'll write down the explicit formula. So these are the general things which have somehow some deeper meaning. Yeah, I don't know actually. Or even their mathematical meaning. So we get these formulas by essentially by brute force. Yeah, it's a good question. I don't actually at this point have any deeper understanding of the meaning of these coefficients. It'd be good to know that.
So
yeah.
And one more question, maybe related. If I just started with some generalized mean fields and then did some conformal perturbation theory or something, just by adding some interactions, I would get some coefficients, presumably, right? Right. I'm just trying to understand whether yeah, this is the same question in some phrased in some other way, which is that if I did conformal perturbation theory, would have expected that this a and zeros, let's say in CFT2 would take this form. That this is the correction. That's
right. So right. So this is sort of what was done partly in this paper by Kirk and company. And so right. So there you normally say is you do some 1/n perturbation theory, and then of course you have to somewhere put in the CFT version of what kind of an interaction vertex are you considering, what derivatives and so on. And so the way that's done is that you say, well, let me do 1/n perturbation theory, but demand that operators up to some maximal spin get some anomalous dimension. And so that's the condition you use to input what kind of vertex you're looking at. And then you carry things out, and then eventually you get these coefficients, but it doesn't look, I mean, it's not a simple thing. The way this is done on the CFT side, it looks pretty ugly because it comes from expanding blocks and so on. So it doesn't look, it looks considerably less group theory-ish and elegant in that way of doing it. It looks much more messy. Yeah, so that at least in existing literature, that does not shed light on this question. But this, part of the reason I like this is this fact that these appear here in this simple form as expansion. It sort of tells you what these coefficients really, it gives some hint that these things must have some nice and definition. But I think, yeah, anyway, as far as I know, that is missing in the literature so far. Okay. Right, so let me say a little bit how the strategy works for the case of derivative interactions. And so here, right, so again, if you have a derivative interaction with two p derivatives, then that can give rise to anomalous dimensions with double trace operators with non-zero spin, but the maximal spin here is related to, maximal possible spin is related to the number of derivatives by this formula. So, you know, it depends what kind of interaction vertex you write down, whether it actually gives that maximal spin or not. So if you want to get so an example of a vertex that does give the maximal possible spin for the number of derivatives is this thing. So you have some phi squared here, and then take j derivatives of phi, and then contract all the indices here in the obvious way. And that will give rise to anomalous dimensions up to spin j. And so those anomalous dimensions were computed again in this paper of Hume's Kirk et al. And the way they did that was with a 4-point function, then they used some Regge limit, because the Regge limit is the way of extracting out some expansion spin, essentially. So it's a great expansion, expanding out the maximal spin contribution. So that's a lovely computation, but it's relatively demanding, a fair amount of technology again, and it's skill and so on, which these people have. But anyway, so the point here is this is quite simple and straightforward to reproduce that in this approach. And well, so I mentioned this already. So what it comes down to, the end, well, all it comes down to when you just trace things through and repeat the previous strategy is this exact same kind of steps as before, things I'll mention, except now you have this more general identity, which I mentioned before. So an identity involving derivatives of propagators. And again, if you know those coefficients in the expansion, the anomalous dimensions are just given by some overall simple prefactors that came up before, and then but all the real information is just in those coefficients. So again, with these things here, those expansion coefficients are the real data here. So how do you, okay, well, those are the coefficients. I'm not learning too much about looking at that, but anyway, there's again, just spray of pock hammers everywhere. Okay, so let me just mention the general strategy here, how this works. So suppose I have a single scalar field, and I just write down here the most general quartic content interaction with some number of derivatives acting on each phi. Okay, so I proceed as before. I compute the first order correction of the partition function. So I bring things down and then do Wick contractions, and I'll get products of propagators now with some derivatives acting on these. So I have some product of derivatives, a product of propagators with derivatives, and the indices here will be contracted in some way, but I'm now like opening up the indices. So I'll do some manipulations with the indices opened up and then contract them later on. And so again, as before, now I'm going to take this product here and expand this product in terms of single propagators. Since there are these indices flying around here, the expansion will now be in terms of not scalar propagators, but spinning propagators, in particular of propagators of symmetric traceless tensors, because that's what appears in the product of two scalars. So you want to take a product, so the mathematical problem is take a product like this, expand this in terms of a sum over propagators of symmetric traceless tensor fields and derivatives of those guys. If you can do that, if you can expand this in that basis, then the coefficients will just be the anomalous dimensions. So the expansion coefficient in front of the spin p propagator will give you the anomalous dimensions for spin p double trace operators. Okay, so this point is boiled down to very well-defined mathematical problem, and to carry it out, and so it actually works out more simply than you might expect, because if you're familiar with this, the actual propagators for spinning particles can be a bit hairy, and for these symmetric traceless guys, there's this nice paper of Costa and company where they work this out, and it turns out we only need some very simple part of that information. So let me just mention how that works. Well, one thing is, so in general, a massive symmetric traceless tensor field in AdS there's no simple action you can write down for that. But the
sorry, I think your screen is stuck again.
For a second, yeah, thank you. But the equations of motion are simple. Okay, so it's just the wave equation with some sort of delta function source. I'm reading schematically here. I'm not writing out indices from the right hand side. And these guys are divergence free, some source, and traceless. Okay, and the mass of the field is related to the dimension and the spin. So if you want to know one of these propagators, what you do is expand out in some basis, during bitensors, and then try to demand that expansion obeys these equations. And what these people showed very nicely is that, in fact, eventually it gets kind of complicated, but in fact, all the information is in principle captured by the scalar propagator. So you write the scalar propagator, and then all the other terms appearing in expansion are just given iteratively in terms of the scalar propagator. Given iteratively in terms of things that get a little bit messy, but it turns out very nicely for the calculations we do here, you only actually need that G delta. So in fact, at the end of the day, everything will be expressed in terms of the scalar propagator. And just due to the fact that ultimately the spinning propagator is expressed in terms of the scalar propagator, it turns out that even though we don't have to actually use all those relations, only the scalar propagator is actually needed. So things are a lot simpler than they might expect. So I realize I'm running a little bit long time, so I apologize if this is tax your patience too much here. But let me say a few words about this. So how that comes about. We only need the scalar propagator. So okay, so in this paper, they do things in embedding space, where we realize AdS is this hyperboloid. And then rather than work with indices all over the place, it's nicer to work with contractings with polarization vectors and to work with polynomials in those polarization vectors. So we introduce polarization vector W. And since we're dealing with traceless tensors, we can allow those to be null, that vector information. So so this tensor is now replaced by this polynomial in terms of these null tensors. Okay, and so then what they did in this paper is they write down some ansatz for the propagator, and there's some basis here. This is in terms of a convenient basis where you have, so there's one dot products of polarization vectors at the two endpoints, and then in terms of derivatives of these functions. And what they showed is that the lowest term in this expansion, the k=0 term, is in fact just the scalar propagator. And as I said, all the other functions here are given by iteratively, G, you start working up k+1, k+2, et cetera, by some equations you can solve and build up the whole propagator. But we only need, as I said, the lowest one. So so what you do, hopefully I just give you just enough, you can kind of imagine doing this ahead, even though I'm not showing all the details, is that, so we needed that product of two propagators with derivatives. So we express that product, we multiply by all the polarization vectors to get something involving the W. So here's the thing we started with after doing the Wick contractions. And then, so we first write this as a sum over sum of these guys acting on some functions here. And then each of these terms here, we then go and expand these in terms of spinning propagators and derivatives of spinning propagators. Okay, so it's useful to do this two-step process for technical reasons that I won't bore you with here. But each of these steps is completely straightforward. You get just a bunch of algebra from, well, you can see there's a bunch of things flying around, but it's really quite straightforward. So once you get down to that, once you're at this form here, this is what we want, right? This is an expansion in terms of propagators their derivatives. And so then you want to integrate this thing over AdS with endpoints separated by one thermal translation. And then these derivatives here, you can just basically do integration by parts and the field equations to remove the derivatives. You can just replace derivatives by field equations. You'll get some prefactors. But after you do that, then at the end of the day, all the derivatives are removed by using those field equations and so on. And so then you just get purely, under the integral sign, you have purely expansion in terms of propagators, and then you just look at each coefficient of each term, and that coefficient will just give you the corresponding anomalous dimension. So it gets, right, so yeah, indeed. So that with that one particular vertex that we're down at the beginning, you have quickly here. So if you want to, you get J derivatives acting on the first G, another J derivatives acting on the second G. Expand this out, and so I wrote this term here is the term of maximal possible spin. So that there's a spin J appearing here, correlated to this guy. And this term is especially easy to pick out because when if you compare tensor structures of the two sides, you can see that in the previous expansion, there's this term, there's the product of two polarization vectors to the power J. And you can sort of directly compare on the two sides that coefficient without having to go through all the summation stuff I talked about before. It's quite easy to read that out. And that would lead very quickly to this relationship here that these coefficients are just given by the coefficients in this expansion. And so then it's just a question of computing those coefficients. And once you do that, then you get the expansions. So then once you have that, once you have this term here, then you say, okay, I want to go to the next one, the next lowest spin. And the way to do that is you can basically, the propagators themselves are divergence free. And so you can just take the divergence of both sides of this equation, that will project out this guy, and then you'll have a term here, the next one, and then you just repeat the story. So then you get the next highest one, and then you just repeat the story for before. Each step, you compute the highest spin contribution. And it turns out if you do it this way, you only ever need identities involving the scalar propagator. So everything is known. So anyway, so we carried this out for that example, some other examples of vertices, and then, so I should say, so if you do this in the other way, so examples like these vertices and so on, in the literature you only find results before for like the simplest cases like 2 and 4 dimensions, where the blocks and the propagators and so on are known simple forms, but you do it, the way we're doing it, things work equally easily for all dimensions. There's nothing special about one dimension or another, really. And so you can easily generalize these results to arbitrary D, and of course check that they match those results for the many cases. Okay, so now good. I'm basically at the end. So some comments. So at least for these contact diagrams with these the derivatives, this turns out to be, I think it's fair to say, this is like the most direct, I think also the simplest way of extracting anomalous dimensions. Of course, there are many ways more interesting. The contact interactions are these exchange diagrams like this. And at the moment, the most efficient method for doing this is using the Lorentzian inversion formula, where you the results you get out are relatively complicated, but that's life. So you have to do something like 4F3 geometric sums. And but so we've only done this just only for some cases, but interesting. In some cases where we've applied this method, you actually get, for example, we've done it with like massless scalar exchange, and you end up getting results. The answers come out in a simpler form, and it's actually quite non-trivial to show the equivalence of that to the known results. So you get some 4F3 from the inversion, and then, for example, for massless scalar exchange, you get something involving like digamma functions, and then search enough around in the Russian math literature, you'll eventually find some crazy identities involving 4F3s related to these other ones, and then papers written about these identities. So underneath the hood here, there's actually a lot of interesting mathematical identities that could be rooted out if one had to organize this. So I think there is something powerful there. But anyway, but it remains, we don't have a story here for the general exchange diagram at tree level, so that hopefully that will exist, but it remains to be seen. And then of course there, you'd like to know, is this going to be useful? You go to loop order and considering fields, external fields that have spin and so on, could be useful there. And potentially could be a big help because you start turning on spin, then the propagators and the blocks and so on start getting really, really nasty. As any simplified methods there would be very welcome. So, okay, that's all I have to say. So, thank you for listening.
Okay, great. Thank you very much for the nice talk. Maybe we can unmute ourselves, unmute the microphone, and clap up for Professor Kraus. All right, so this is the time for questions. So if you have any question, please go ahead.
Hi, Per. I was just wondering whether, I mean, if we use this technique to get the anomalous dimensions and then go back to the 4-point function, does it become simpler to extract out the OPE coefficients rather than solving the original 4-point function for the couple set of questions of solving both the OP coefficients and the anomalous dimensions?
Yeah, I sort of wondered about that. I haven't actually tried it, but I think it's not obvious it leads to a huge simplification because those contributions come from sort of different places. So you get like some logs that you use to look at the anomalous dimensions, logs that come from expanding the blocks and the dimensions. So you sort of use that to isolate out the dimensions, and then the OP coefficients sort of come from a different part. So it's not completely obvious to me that that would be a huge help. But I have wondered about that. So it would be very nice to know. So the short answer, I haven't really tried to do this, but it would be extremely nice to know whether ultimately the OP coefficients could again be related to these AN coefficients in some way. That's about all I can say. So one would have to try, I think, actually work on an example, but the stare the formulas is not immediately apparent. There's some simple way to get it.
Yeah, no, I mean, given that the ANs probably have some group theoretic meaning, and the C's are some kind of 3J or whatever, 6J symbols or something of this conformal group. Also the yeah, I mean, the conformal bootstrap equations constrain the two of them very tightly. So you might think that there's implicitly some relation between the two, which is
right. And there's also, I mean, a hint of that. There's this famous, derivative relation, which sort of popped up experimentally in a paper, which relates the correction to the OP coefficients and the anomalous dimension. Like one is like the derivative of the other with respect to the dimension, and so that's sort of just been observed from the results, but hasn't been. So that if you know it's true going in, that gives you one simple way, at least for some interactions, of getting one for the other. But it's not known, why that holds. And so perhaps, but that's a strong indication that there is something going on along the lines of what you said. So yeah, actually, then now that I remember, that's there must surely be something there, some nice formula that will explain that the relation between these theory structures.
Hey, one question. Thanks for your talk. That was nice. If you wanted to go to higher order in coupling, then you would have to do you have to take like bigger products of these propagators? You had this propagator identity where you took a product of 2 propagators. You'd have to take products of more number of propagators, right? And
that's right.
Others,
yeah.
And other such identities which you can use to go to the next order.
Right. So you need a bunch of new identities, and so so I don't know those identities at the moment, and I think one can just search for them by complete brute force, but clearly the way to do this is to better understand why these identities, in the case we've done, exist, and so what their meaning is. Otherwise, one is searching in the dark. So, so anyway, yes, you will need new identities, and in particular, once you have exchange diagrams and so on, you'll need identities that somewhat involve possibly things involving integrals of these propagators or multiple propagators with points at various locations and so on. So at each new step, you'll need some new identities, and so one needs to know what the what is the reason for these identities to exist, and then but that has not been done yet. So.
Thanks.
Any other questions?
Hello. So you had mentioned this, like somewhat tangentially, but can you say more about how this method of decomposition, how does it work with this large J expansions and so on? Like, do these decompositions become something nice in large J, or what is the?
It's a large spin. Yeah. So things are, so the statement here is that, so a couple of things. So one is, so there's a lot of literature about doing things like large J expansion and so on. So most of that, and that's what is underlying a lot of, say, things like the Lorentz conversion formula. So a lot of that is based on this analyticity and spin, the fact that the CFT data is analytic and spin. But to say analytic and spin means it's, so this has to, so these contact interactions give rise to anomalous dimensions with bounded spin, okay? So there's no analyticity and spin for contact interactions. It's where you have exchange interactions. Exchange interactions give anomalous dimensions for all spins, and the statement is those formulas are analytic and spin. And so if analytic and spin, you can do a 1/J expansion of those analytic functions, and then nice things happen. So here, there's not the same story what I talked about here. So here I talked about doing something with the highest spin. It's not really a large spin expansion. It's just saying I'm starting at the highest spin, and then working my way down. So it's basically that. So it's not really. Yes. So what I'm doing here is not really related to what you'll find in the CFT literature, where people talk about doing large spin perturbation theory. That's what I'm trying to say. It's a different thing. That might come once we discuss these exchange diagrams. Then we can try to make contact with that in here. Here, this is the statement. If I start from the maximal spin and go down, it's just the way that these all these tensor structures appearing in the spin propagators. It's just easiest to sort of pick out the highest spin contribution first, and then work your way down. But it's probably not unrelated at the end of the day to what you do in some 1/J expansion, but it's a bit of a different thing.
So one more question, which is also related to this question about going to higher order in lambda. Like, you think like this can be used to say something about let's say 3-particle states and so on. Let's say if I had like some 5^6 or something. You think that can be?
Yeah, definitely. Yeah, no, there's some very simple things you could do that basically one could immediately do. Yeah, so there are, you can definitely say for like 5^6. In fact, there I think the identity is known. So there you need some identity involving the product of 3 propagators. And I think actually in one of the papers by Fitzpatrick and Simmons Duffin and sorry, I'm blanking on this. I think they considered such a thing like 5^6, and part of solving that problem, there's some early paper where they considered sort of old-fashioned perturbation theory, quantum mechanical perturbation theory, and they use such a relation. So yes. Anyway, so one could definitely work out such things. So for just a contact interaction involving n fields, it's actually these methods would go through relatively straightforward. Although I don't know what the general form of identities would be, but in any case, yes, that could definitely be done.
There's one more question, and I'll stop. So is there some simplification which appears if you have like two deltas, one of them being much larger than another, like where you have one heavy particle and the other particle is like going around?
Yeah. Yes, I mean, there would, I haven't looked at that explicitly, but the answer is definitely going to be, I mean, the simplification that happens basically, just conceptually, is that this particle that's propagating along, it's very, very heavy. Instead of its world line wandering around, it's just going to be sort of pinned to the origin of AdS, right? AdS is at some potential well, it's very heavy, it's going to sit at the origin. So effectively, you just have some static object sitting at the origin, and then it's so there'll be some other particle effectively moving in the background of that static object. So so one could definitely arrange things that way. It depends on, the examples I gave here, everything could be done for arbitrary masses. There's no reason to do that, but if you went to some more complicated calculation, higher orders and like that, it may be quite useful to do that. But yeah, so anyway, so things definitely simplify a lot. Yeah, you reduce the number, every heavy dimension operator, every heavy field effectively becomes non-dynamic with some fixed background. So that helps.
Okay, thanks.
Any other questions? All right, I think there are no more questions. So thank you, Professor Kraus, once more. So
yeah, thank you for
yeah, so that's it,
speak and just,
that's it from us. So thank you very much. Thanks once more. Have a nice time.
okay, good night.
Bye.